talking about today. I was going to say put your hands up, but there's not much point with. They don't have dimming lights here. I'm going to turn this up for a moment. Don't worry, this goes on for 5 minutes. You're not going to miss much. Who knows what a 2024 YR4 is? I wanted a better information. Go on, yes, you do. Who's heard about the asteroid that's going to crash into us in 2032?
Maybe the moon as of this morning.
Right. Can you bring up the Patrick on the screen? There's Patrick.
Hello.
Hello. We're joined from France by Patrick Michel, who is Europe's lead on whether we're going to die because of asteroids. And you've just come out of a meeting.
Yes, I was at the steering committee of the International Asteroid Warning Network, where we discussed the 2024 YR4 and the fact that now the probability is going down drastically. Now it's about 0.2% and should still go down. So we are basically safe from this asteroid. In case you're worried, we are not really worried. Now we can say that.
Hey! Well, we can go home now.
No, it actually demonstrates that the international coordination that we have set up to take care of this risk is very reactive and efficient, because immediately after a threshold of 1% of probability was reached on the 27th of January, immediately we reacted, we met, we organized observations so that only 1 month later, even less, we could basically remove the problem. So that's a good thing.
Yeah, science has worked amazingly well. I think telescopes and the Newton's laws of gravity basically have fixed it all. We're also joined here by two UK experts on my, well, they're both on my right. This is Stefania Soldini, who has landed robots on an asteroid.
Far too much.
You did, you landed it.
It's amazing. No, we'll see some slides, I hope, about this.
You're really a journalist.
And also Ashley King from the Natural History Museum, who has, well, actually, so you landed stuff on Ryugu, which is, if we go back to this.
I was in the team.
I know you were in the team, but you're the only one on the team who's here. And you were programming. You were programming the landing. We will get to that. But did you ever get to use any of the Ryugu?
I've looked at Ryugu, under the microscope in the laboratory. So I study the rocks that come back from these asteroids. I'm really interested in what these things are made of.
And so we've got a fantastic collection of experts here, and these two are both UKRI Future Leadership Fellows, of which there are very few, and there are even fewer in astronomical sort of sciences, and you've got them both here. So immensely privileged, and Patrick Michel, who's a fantastic advocate for all of this.
The French guy, you know.
Can we go back to the slides a moment? So, if we look very briefly here, I don't know, Ashley or Stefania, some of these objects are the things which are going around us, which are going to be interesting. Earth is in blue. There's Ryugu going around, which you can see goes around, what, every 2 years or something?
Yes, that's right.
And also Bennu, which is an asteroid that a NASA mission went to, and you've also, I saw some of that when I was with you.
Yes. We've looked at Bennu.
The reason I actually wanted to talk about this was because of this, set this whole thing up, is because of this other one called Apophis, which is right at the top, who is a god of doom. And when it was first discovered about 20 years ago, there was a bit like the panic just now, this idea that in 2029 it was going to crash into Earth. Good name to call it. The news is, well, I'll let Patrick just call out. I presume we can hear you.
Yeah.
Yeah.
Yeah. So if you want, actually, it's a good example because what was missing is exactly what we were able to do for YR4, which is that when we discovered Apophis on December 2004, we first had an impact probability with the Earth of 2.7% for Friday, April 13th, 2029. So Friday, April 13 is not very good. And in fact, it was very short because immediately the day after, we could find other observations from June 2004, and taking the two type of trajectory, we could eliminate the probability of collision for 2029, but we'll still see it with naked eyes. We can come back to that. But in fact, when we had this probability, we are thinking, who are we calling? Wow. So in my case, was the President Jacques Chirac. My American colleague was George Bush. Anyway, so we are starting to see that there is a missing link between the people like us, we can predict something to happen, and the decision maker that who can implement a response. And that's why we went to the UN and started to get organized with two groups, which were the one that took care of YR4. So Apophis was really the first, let's say, case which made us aware of the gap which was between the scientist and the decision maker, and hopefully we start to be better with this.
So this is what got me interested in the subject, was because it could be going to hit us. The news is it will not hit Earth, but it will come closer than some satellites. And so Patrick is incredibly involved in the idea of actually trying to catch up with it, which is much harder than you think. Something which is just above our head is something much harder to do than, I don't know, the sort of simple stuff you did, landing on an asteroid. But what an opportunity to try and work out what these things are like that are coming close to us. So I joined Patrick and a bunch of people. Stefania was online last year at a big meeting where they said, how can we make the most of this idea that an asteroid comes this close, but actually isn't going to hit us? So that's the backdrop to all of this. I can't remember what I've got next here. Why don't you bring Patrick back up again? So, in the olden days, I'll come back to you. Sorry, Patrick. In the olden days, the way that we would understand asteroids would be what Ashley does. You've got some stuff in your bag there.
I do. I can pass these around a little bit as well. So I work at the Natural History Museum. I'm very lucky that I'm locked away in the basement. I don't get out very much. I don't get to see people very often. But down in the basement, we have the National Meteorite Collection. So we have about 5,000 pieces of meteorites from about 2,000 different meteorites. So worldwide, we have something like 80,000 meteorites in our collections. Nearly all the meteorites come from asteroids. So they come from bodies like Bennu and Ryugu and Apophis. And they give us a kind of hands-on way of studying asteroids and what asteroids are made of, what their kind of chemistry is, what their structure is. What I'm really interested in particular is using these to understand how our solar system formed. So asteroids take us all the way back to the start of our solar system. They're like the leftover building blocks for making planets. So we can't really do anything with the Earth now because we're an active planet and we have plate tectonics, and all the rocks that were there 4.5 billion years ago have been reprocessed and melted. But asteroids are accreted right at the start of the solar system, and pretty much nothing's happened to them. And then occasionally they collide into each other and a bit goes through and it comes to our atmosphere and we get to collect it. And so I have a few that I will happily pass out if people want to look at. So this one is a piece of an iron meteorite. I have to get these back at the end. I will be checking everybody before.
The librarian will buy on you.
This is an iron meteorite. This is what we call a stony meteorite, or sometimes we call it an ordinary chondrite. So out of that 80,000 meteorites, about 90% of them look like this type of rock. And what you'll see is it's a piece of rock, and if you tilt it, there's a little bit of metal in there. And so that's basically the starting point for our solar system.
And I mean, did you bring it? So
I will. I won't hand this one out, but people can see this at the end.
But you might remember that it's in 2021.
2021, yeah, we're coming up to the anniversary actually in end of February. So most of our meteorites look like this one I gave out here. We have these iron meteorites. These actually do come from kind of like protoplanets, so things that got big enough that their insides got hot and they melted the rock. But they weren't as big as, say, the Earth, and so they cooled down very quickly, and so you end up with these kind of lumps of metal. So it's like having the core of the Earth that we've got there. And then we have some really, really rare types of meteorite that are similar to the things that we get from Bennu and from Ryugu. And these are our carbonaceous meteorites. And so this one is a little piece of a meteorite called Winchcombe, which you may have heard of. You can hold this one. So Winchcombe landed quite famously, I think now, on a driveway in Winchcombe, which is not so far away from here, and just went splat. These are very soft, so it wasn't a big meteorite at all. So that's why most of what we've got are these tiny, tiny pieces. But these are amazing. These are rocks that contain carbon. So it has, when you come down and see it, it's really, really dark. So it has about 2-3 weight% carbon in it. And that includes organic materials. So it doesn't have life in it, but it certainly has the kind of building blocks for how we might start thinking about how life formed. And it also has about 10% by water. So not liquid water kind of sloshing around, but it has it trapped in its minerals. So this comes from an asteroid that 4.5 billion years ago had water reacting with rock. So this tells us where water came from in our solar system.
And I just think it's amazing that, that was, I guess the two things we knew about asteroids were the things that burned up in the atmosphere and presumably pretty much the way they were before they came through the atmosphere. But I guess there's always a concern they've been altered a bit in the fireball process.
So yeah, our meteorite collections are completely biased to things that will survive coming through the atmosphere. So that's part of the reason we have more of these rocky ones than we have these kind of carbonaceous type rocks. And then every meteorite, I love meteorites, they're amazing, they tell us so much about the solar system, but they're all contaminated. Every meteorite comes through the atmosphere. They are coming in from space. So you've probably heard of shooting stars or meteors or fireballs. That's space dust and space rocks coming through, and you get this bright streak in the sky. It only lasts 4, 5, 6 seconds, and the outside of the rock gets hot. It melts, and we end up what we call a fusion crust on the surface. But the inside stays completely unmodified. Rock doesn't conduct heat very well at all. And so actually everything inside is really pristine. But when it lands on the ground, especially Winchcombe, which went splat all over this driveway and we were sweeping it up and picking it up, they react with the terrestrial environment. You want to collect these things as quickly as you possibly can, but actually most meteorites are found thousands and thousands of years after they've landed on the Earth's surface. We don't see them landing in any way. Winchcombe's a really special case where we actually have a network of cameras here in the UK where we kind of watch the skies and we look for these meteors and for these shooting stars coming in. And we can work out sometimes that there's a chance of a meteorite landing. So we didn't know which driveway, but we had an idea. We knew something could come down, and we knew Winchcombe, actually, we released a kind of big area, big search area. And just by coincidence, Winchcombe was right bang in the middle of that. And then we were really lucky that the family whose driveway it landed on collected that material within about 12 hours.
Did they have a doorbell camera as well?
They didn't, but people do catch these things on doorbell cameras. Yeah. So if you've got those like Ring doorbell things, they pick up meteors really well. And we have a network of cameras, of kind of specialist cameras as well that do that. So basically what we can do with the cameras is we can work out if meteorites are coming down. We can calculate roughly where they may have landed, but we can also back out the orbit. So we can work out the journey it was taking around the sun. So we can't say exactly which asteroid, but we can say maybe whereabouts in the asteroid or in the asteroid belt or the solar system it came from. But we have that information, those orbits, for about 40 of the meteorites in our collection. So it's really, really rare. So basically, I'm a geologist by training, and what I've got at the museum is a collection of random rocks that come from space. But I have no context. I have no information about where they came from in our solar system.
And then the
By
other
the way,
thing...
you know...
Oh, sorry, go on, Patrick.
You know that in France, there is a meteorite that fell on the roof of the house of a lady. And guess what was the name of the lady? Mrs. Comet.
I hadn't heard that.
and for the people who have these meteorites in their hands, in particular the ordinary chondrite, you should realize that you have in your hands the oldest material of the solar system. Yeah. Because on some of these meteorites, I don't know for the one you have, we have the material that allowed us to date the origin of the solar system 4.567 billion years ago. And this is because the material you have in your hand are the first solids that condensated in the gas that formed our stars and the solar system. So touch them well, because these are the oldest pieces. The older one on Earth is much younger than that.
Yeah, that's amazing. look after.
Yes, this is,
It must be very expensive.
Doesn't leave my side.
But I was going to say, otherwise, all you see is a dot in the sky, which is what asteroids look like, orbiting around the planet, until people like Stefania and her colleagues.
Yeah.
So you went to see. Let's see if I can bring up some of your slides, Stefania. So this was a Japanese mission that you worked with. I'd love to know
This is
how you.
Osiris Rex, actually.
Yeah, okay, well, they're all in the wrong order, of course. We'll skip past that. And we'll get to Ryugu, Hayabusa 2.
Oh, yeah.
So actually, you can see them, can you?
Yeah. So, well, Hayabusa 2 is a Japanese mission that is still active, which is important to remember, and return sample from asteroid Ryugu, but they did much more than just returning samples. So a lot has been done, and a lot has been learned from an engineering perspective. So Hayabusa 2 was, because it's not equipped anymore, with a lot of different deployables. They shoot the asteroid to try to collect material under the surface, which is what has been returned by the sample. There has been also the deployable Orbiter rover on the surface to demonstrate possibility to do motility, and some picture has been taken closer to the surface. The impact, the little impact, not like that, we can talk later, was observed by a deployable camera as well. So from an engineering perspective, that was quite a complicated architecture.
To me, it's like a Swiss Army knife mission. I mean, it just had so many different bits.
Many gadgets,
I
let's
think
say.
you're downplaying it still. So
No, I don't.
Ryugu, this asteroid it was chasing, is how big?
Gosh, don't remember.
It's
anymore.
about 900 meters.
900. Oh, so it's quite a big one. Okay, it's on an orbit which is quite like the Earth's sort
Yeah,
of.
I mean, those that come near the Earth usually are quite, you know, you didn't need to chase them at the right time, but yeah, they share a similar orbit.
And so I did have at one point a slide. So the mission had to go around the Earth about 3 times to catch up with it.
Catch up with it. So yes, so this is quite the beauty of it, of trajectory design, because it's not just a direct journey, but you need to take advantage of close approaches with the Earth and get more gravitational pull to actually get there. And then after the return of the samples, actually in 2026, Hayabusa 2 is going to visit another asteroid, and then in 2031 is going to visit another asteroid. So there is still enough fuel left to actually go and keep exploring, which is, I think, is fascinating because it wasn't designed for that.
But you were sort of following, basically you were fellow travellers going around Ryugu and Hayabusa 2 were just sort of travelling around the sun at the same time.
Yeah.
And you were sort of peering on this side and that side, and then you went down a bit closer.
Yeah,
and
so the type of operation that Hayabusa does, which is slightly different from Osiris Rex, so depending on the spacecraft, how they design, the way in which you approach the surface could be different. So Hayabusa 2 was doing what is called hovering, so basically maintaining a fixed geometry with the Earth and the spacecraft and the asteroid. So always pointing at the camera of the asteroid and solar panels towards back, the antennas toward the Earth. And so all the operation started from 20 kilometer distance and went down basically to the surface using LiDAR to kind of have an understanding how far they were going. So this kind of example.
Oh, there's
This is Apophis, yeah.
Oh, that's Apophis. So that's going to look for that video. Oh, this one.
Oh, yes, this is an example of rehearsal operations. So one important thing to remember, we didn't know that Ryugu was going to look like that when before arrival. So everything gets designed with some knowledge of what we think the shape of the asteroid look like from radar observations. So first of all, it's super exciting when you get there and you see the first images of actually how this new rock looks like. And before doing operations as, let's say, as complicated like touchdown and for collecting samples. So Hayabusa 2 did the 2 touchdown. There is also what is called rehearsal operation. So this was actually real images approaching the surface and just rehearsing the most critical phase. So seeing it, because the last bit of the operation was done autonomously. So you need to trust that everything is calibrated correctly so that it doesn't crash on the asteroid.
Well, I think it's incredible. So at the time when you were doing this, was the Earth and Ryugu close together? I know at some points that you were on the opposite sides of the sun almost.
So there was a time which in between, that one, I don't remember precisely, in between the 2 touchdowns, that the sun was in the way. So the sun, there was an alignment between Earth, sun, and asteroids. And there was a time where we kind of would have lost 1 month of communication with the spacecraft. Now, maintaining the spacecraft 20 kilometer distance from the asteroid requires like routinely adjustment. So you need to maintain it there. So like every 2 days give some maneuver to keep in that position. Now, no one trusted the spacecraft to do that for a month without ground support. So the idea that for which I was the designer of that trajectory phase was to decide what to do with the spacecraft for 1 month without being able to actually give any command. So what I came up with was putting in a safer distance, basically. And that's actually worked quite well. We then took the chance to do what is called radio science, so try to see, can we interpret anyway some signal from the spacecraft in those situations? And that's helped to understand more how radio communication works when you have the sun in the way. So what I love about Hayabusa 2, but also I'm pretty sure OSIRIS-REx and all these missions, you take any opportunity to just try to push the boundary of the technology and try to understand how we can improve the way we do these type of things. So it's
and an incredibly important part of it is that you sort of send the instruction, do this, but it has to then manage everything itself. It has to have the computers on board to understand the images and the distance and all that kind of stuff.
It depends how critical in the operation, because there were 40 minutes delay communication in the case of Ryugu. So you send the signal, 20 minutes later gets to the spacecraft, and 20 minutes later you check what has happened. So that is quite scary. So if the operation is not critical, you can do that just by planning. So you work on your computer, set the maneuver, and send it to the spacecraft. For more critical operation, like touchdown and sample, that has to be all pre-planned. So it's a series of commands, and you just finger crossed. But there were actually, some checks. So the spacecraft had the means to decide at some point if something wasn't working right to abort the operation. So that's good.
But I think this is all incredibly important. If we go back to the idea that one of these things may hit us and you may want to do something about it, to have the experience and the knowledge about how to do this kind of navigation. I'm going to bring Patrick back now, if you can. Where are you? There you are, Patrick. Because, we keep on talking about OSIRIS-REx, which is a NASA mission, but I want to talk about Hera, because in a sense, I suspect quite a lot of what Stefania's been talking about is relevant to, well, explain what DART and Hera are about.
Yeah, well, in fact, first I would say that I have a really high recognition for the engineer that made the operations of Hayabusa 2 as well as OSIRIS-REx, because they were faced with something we may be faced with Hera, is the fact that all the assumptions that we gave them to design their operations were wrong. And that's, the scientist has always a good role, because if he's wrong, he's happy because there is a new challenge. If he's right, he's also happy because he predicted something. So we are always happy. However, the engineers, they have a problem because, for Ryugu, for instance, because he was the first before OSIRIS-REx. OSIRIS-REx was prepared because Hayabusa 2 arrived at Ryugu in June 2018. And OSIRIS-REx arrived at Bennu in December 2018. So they could learn already from the surprises of Hayabusa 2 how to get prepared. And in fact, what was found in the first image is that there are many more rocks on Ryugu than we thought. We told the engineers, don't worry, if you have an accuracy of 50 meters to go down and take a sample, that will work. There will be sand beaches like in Brighton or in Nice, no problem. Well, in fact, we arrived and there was no beach at all. It was just rocks everywhere. So first of all, we had to understand the height of the rocks because there was a constraint that we should land where there are no rocks with a height higher than 1 meter. And then we realized there is no area as large as 50 meters without such rocks. The largest area was 10 meters. So they had to sacrifice one sampling operation in order to revise entirely their strategy to be able to increase the accuracy of landing because our assumption was wrong. So talking about DART and Hera, we already had the same surprise with DART because DART is basically a mission which launched a spacecraft, the whole spacecraft, solar panels, everything, on an asteroid at several tens of thousands of kilometers per hour, 6 kilometers per second, 580 kilograms. So I know your units are maybe not the same as mine, but you have to convert kilograms and etc. But anyway, so a big, let's say, a washing machine with solar panels eating very quickly on an asteroid as small as 150 meters. So 150 meters, that's very, very small. It's like a stadium of football. And doing that, like Stefania was saying for Hayabusa 2, autonomously, because the impact occurs at 11 million kilometers from Earth. It's impossible to use a joystick to direct this spacecraft, and it had to recognize by itself with this camera and a smart navigation system the asteroid and eat into it. So that was done by DART. It was actually an asteroid evolving around another one. It was a small moon, like the Earth and the Moon. And the plan was to modify the time it takes for the Moon to go around the main body and to reduce it. We didn't know how much we would reduce it. And we did it at an epoch, 26th of September 2022, when the asteroid was close enough from the Earth that we could measure this reduction of time it takes for this small 150-meter moon to go around its main body. And we call that the orbital period, the time it takes to make one turn.
So you could see if you slowed it down or sped it up just a tiny bit, and that was you could get an idea of what happens when you hit an asteroid.
Yes. So you want to say, so we take a spacecraft, we hit into it, and then this little moon that was going around with 11 hours and 55 minutes, after the impact, was going around with 11 hours and 22 minutes, meaning that we reduced the time to go around the other body by 33 minutes, which is quite large, which is great, but that's the only information we have from DART, because, and of course, the images before the impact showing us a surprise that despite the fact that it's only 150 meters the size, it is full of boulders on the surface, like Ryugu. And why is it surprising? Okay, for us, we expected something like this, but still, it's because if I'm on this asteroid, 150 meters, the attraction is proportional to the size. So 150 meters is very small. When I am on Earth, to escape from the Earth, I cannot with my legs. I need a rocket because the Earth is super attractive. On this asteroid called Dimorphos, just jumping on my chair like I do, I would already be in orbit because there is no attraction. It's very small. To escape from it, I don't need to jump. I just walk and I go away. And despite this very low attraction, there are a lot of boulders on the surface. So that was the first surprise. Now, what happened with DART? We don't know. In terms of, did we do a crater? In which case, what is the size and the depth of this crater? Or did we entirely reshape this little moon? That we don't know, because we didn't have any orbiter to observe the outcome of this impact. So this is where Hera comes. Hera is a sort of a detective, I don't know if you know the Colombo detective in the series, which goes back to the crime scene in order to tell us what happened. So that we can use this knowledge to extrapolate to other scenarios. We do impact modeling. Actually, in UK, at Imperial College in particular, you have great experts of the modeling of impact physics. What happened when we hit another rock with a projectile? What is the outcome? But they need to have validation of their models at the scale of an asteroid. And the validation consists of using the same initial conditions at the experiment, so basically the size of dart, the mass, the speed, using the same properties for the target as the one we observed, and then check that what they have in result correspond to the reality. And the reality will be given by Hera. Do they have to reproduce a crater? Do they have to reproduce a totally reshaped asteroid? So that's why we launched Hera on the 7th of October 2024. It's the first time in Europe that we send in deep space for asteroid exploration a mission that consists of a main spacecraft and 2 CubeSats that will be deployed at proximity of the asteroid to do operations at closer proximity. So CubeSats are sort of a shoebox-sized little satellites with their own propulsion, own solar panels, and they will carry out some measurements we've never done before, because one of them has a radar on board that will probe the internal properties of the asteroid, and we will know whether it is a solid rock surrounded by rocks, little rocks and gravel, or whether it is just an assembly of gravels throughout the whole body. So it's absolutely exciting, and with that, we'll offer to the world the first asteroid deflection test, successful and fully documented. And again, regarding surprises, I mean, Stefania and I are looking forward to the first images of Dimorphos, this little asteroid, because we have the images before the impact. And we have predictions of how it looks like now. But knowing the past experience, I'm sure we are all wrong. So that's a very exciting moment.
Stefania, you were involved in DART as well, were you?
So I'm involved in Hera and in DART as in the group of simulating the ejecta. One of the things that Patrick has said is the amazing things to do this experiment in space. We also realized that we knew at least that the ejecta itself gave us an extra push as well. So try to measure how much that effect is helping the deflections is one of the key goals for the DART mission. But that's also the other question we have is when Hera is going to go there, is anything that's been left behind?
I mean, didn't you also have a problem with Hayabusa 2 that you were worried that there may be bits of grit in your way? There was a bit of worry there. The difference with this mission is they're quite a few years apart. In Hayabusa 2, there was like the kind of engineering believed that after 2 weeks, we can go back, everything is clear. But we had to actually verify that. And in that case, it turned out, in fact, even if something might have impacted the spacecraft itself, it was within his design capability to withstand those little projectiles. So the probability was really, really low. In the case of DART and Hera, because these events are happening with a few years of distance, now probably whatever survives has to be large enough. But what it was amazing was the observation of the tails. There were kind of unexpected long time trail, something that probably was still feeding the tails months later, and maybe Patrick can say more about this, but that was kind of a surprise as well, and tell us a bit more about the kind of stuff that came off it, effectively.
Definitely.
I want to actually
what's exciting. Yeah, what's exciting with asteroids is that so far, and there is no counterexample, each time we interacted with an asteroid, the behavior was not the one we expected. So we are still far to understand them. Now we understand better, because each time we don't understand, we are big teams, and we discuss and we understand why we didn't understand. So we progress. But it's true that because they are so small, they evolve in an environment which is so different than the one we experience on the Earth on a daily basis, that it's a sort of counterintuitive. An example is given by Hayabusa 2. There was also on Hayabusa 2 an impact experiment, the small carrion impactor, and I know Stefania worked on the fate of the ejecta of this experiment. So it was this time a 2 kilogram box that was deployed at 100 meter height of the asteroid and exploded to give energy to a projectile of 2 kilograms that was launched at 2 kilometers per second on the surface of Ryugu. And we did impact modeling of this impact. And our prediction was the crater would be 2 or 3 meters in diameter. And in fact, it was almost 10 times larger than our prediction. So another example is Bennu, OSIRIS-REx, when the touch-and-go sampling mechanism touched the surface. With Bennu, we stayed almost 2 years around the asteroid with superb images, because Bennu went into orbit around the body, went at very close distance. So we have documented geological knowledge that was amazing. So you could say, okay, so you understood the surface in that case. No, because when we touched, again, the reaction was not the one we expected, because actually there was no reaction. The sampling tool went through the asteroid, and because the thrusters were activated, we went away again. So like we were going into a fluid. So
like quicksand,
just
someone
to say
told me.
that, sorry?
Like quicksand, someone told me.
Yeah, like a foam, like, you know, the foam you use to shave. very, very soft, very underdone.
Can we just have the slides? Can we just have the slides?
Yeah, you should. I saw the slide, actually. You had a slide with the sampling.
I think it's before this one, maybe.
Yeah.
I think so.
Okay, yeah.
They were
Let's
all
see if we...
all the missions.
I've heard it described as a ball pit. So, you know, those ball pits you get in kids' play centres. It's like jumping into one of those, I think, was how Bennu's surface was described as.
And in fact,
you're going
just
too fast. I think it's later.
You think it's later?
Yeah, I think so.
Sorry. Oh, here we go.
The middle one.
That middle one. So that's the thing that was landing on Bennu.
Yeah, but also if you see evenly JAXA doing touchdown on the left, you see how many material flying off as well. So this is
the bottom line is you cannot trust yet images, because the images may tell you deal with something which is very solid, which has what we call a strength, and in fact, when you interact, you feel no strength. It could have strength, but unless you touch, you cannot verify it. So for me, the bottom line is we need to have a sort of an external action on the asteroid that tell us how it responds. Because if you just have images, you can be misled. We are learning. I hope that with all the missions we have, we live the golden age of asteroid exploration. Little by little, we'll be able to relate images to the mechanical properties of the asteroid. We are not yet there. And talking about Apophis, you see the transition, is fantastic, because here, in the case of Apophis, we don't even need to interact ourselves. Nature offers us the forces that will be active on the asteroid, because when Apophis comes close to the Earth, it will be close enough that the tidal forces of the Earth may, make some reaction of the surface. So we just need to be there to observe. It occurs only every 1,000 years that we have such a close approach of a 340-meter object to a planet. So for us, it's the only occasion, because we won't live 1,000 years. And there, the beauty is that we don't even need to impact it or to take a sample. If we are interested to understand its mechanical response, we just need to observe how the Earth acts on the asteroid, and maybe we'll see a change in the rotational axis, surface motions. And that's why we need to be there, because this is the first occasion we can just let nature do the job for us.
It'll basically make the asteroid creak if the gravity of Earth will make it creak if it's soft enough, basically.
Exactly.
Before we, because we were just talking, we saw those pictures. There's another picture. This is your picture of Bennu touching down.
Yes, yeah. Oh, it's not playing.
And then, so it's another magnificent, a bit like Hayabusa 2. They went there, they collected the stuff, it's sort of shoved down to the ground, they grabbed what they could. Got too much, I think, didn't they?
Oh, you can never have too much. No.
Okay, they got more than they had bags for. And then I always think of it a bit like a DHL delivery. The thing flew past and just dropped off.
Like one of those Amazon drone things. I just want to say to Patrick that when they got to Ryugu and they got to Bennu and there was all the rocks there, I was on my chair jumping up and down because that's exactly what I wanted was rocks. I know the engineers don't want to hear that. So I want the rocks. I want to see the rocks. I want to see how they're related to each other, and then I want a bit of that rock to come back. So both Hayabusa 2 and OSIRIS-REx were sample return missions. So the engineering and the spacecraft and going and working in these environments, they're small bodies, they spin really fast. I don't think we've talked about how difficult it is to actually get a sample off the surface. This isn't like Mars when you can put a rover on there and drive around and do science. It's kind of just grab that sample and get the spacecraft out of there as quickly as you possibly can. The surfaces don't react necessarily how you're planning as well, so you come up with these ideas for how you're going to sample that material, but the surface might be covered in boulders, might not be like a beach, and it might be doing things and softer, and it's really challenging. So Hayabusa 2 brought back about 5 grams from Ryugu, and that doesn't sound a lot, but honestly, you give me one tiny little particle, I could be happy for the rest of my career, to be honest. There's so much information locked up in these samples. And then OSIRIS-REx came back in September 2023, and it returned 121.6 grams of the surface of Bennu. So this is the largest asteroid sample return that we've had so far. And
this is the piece that you got?
And this is the piece that I got. Well, I was actually lucky enough, so you showed the picture of the sample capsule coming back, and so the OSIRIS-REx spacecraft is on its way to Apophis now. It's going to be doing some extra science. It won't be sample return, but it's going to go and look at the surface of the asteroid. And we haven't really visited very many asteroids at all. So every one we go to, like Patrick said, is completely new. We discover new things. But on its way, it dropped off. This is the sample return canister that came hurtling back through our atmosphere, a bit like a fireball. It landed in the Utah. This is a test and training range for the US Air Force or something. So basically, it's a big desert where there's nothing other than a few roads and the occasional landmine. But everything went perfectly. This thing came in, had a parachute that came down. They collected this, and then the next day flew it down to Johnson Space Center at NASA, which is where I was waiting. So I actually got to do some of the very, very first measurements within a day or so, 2 days of this coming back, actually studying these samples. And then, we came back to the Natural History Museum. So this is a huge sample analysis team. There's about 200 of us across the world working on these samples at the moment. We got, I think it's about 100 milligrams. We call it about a tablespoon or a teaspoon's worth of material. But honestly, that's just are those
your fingers there, Barney?
They are not my fingers, actually. This is done, so these samples, I mean, one of the reasons we do sample return is to get pristine samples that haven't been contaminated by the terrestrial environment in any way. And so these samples, the capsule itself was opened in a big glove box at Johnson Space Center that's specially built. So basically, it's a big box where we pump all the air out. So it's full of nitrogen. So there's nothing reacting with the rocks. It's very, very stable. We control the temperature and the humidity and things. These samples were shipped to us under nitrogen, all sealed up. And then we have a glove box as well, a much smaller one, but we have a glove box for our really important meteorites like Winchcombe and samples like this. And so, what you can see, the fingers is one of my colleagues, Sarah Russell, holding this within our glove box. And honestly, these are really difficult boxes to this is a tiny amount of material. Exactly. This is quite... it's difficult. It's hard work and it's very stressful. You've been waiting 10 years for these samples, manipulating these things under these no pressure. Well, almost literally no pressure in the box, but it can be very nerve-wracking and
it costs a lot to get.
And it costs a lot, yeah. So we can pick out kind of little grains, sort of a millimeter-sized particle. We can take it out and then we study it. I use X-rays. I use electron beams.
How easy is it to pick them up?
Yeah, so once you get small, things like static actually kind of work in your favor a little bit. So we often have a needle or something and we can get a grain and particle and we can manipulate it around. The challenge with the Bennu samples and Ryugu samples is that they are mainly clay minerals. So they're a bit like a mudstone that we have on the Earth. So that most of the minerals have OH locked up in them. And so they are really friable, they crumble. You basically kind of have to look at it and it just goes, oh. They're very soft. That's why we don't have very many meteorites like that, because they don't survive coming through the atmosphere and they won't sit on the Earth for very long. And so, yeah, not easy to handle, not easy to manipulate, and sometimes you want to polish them, they don't do that very well. So actually, difficult samples, much harder to work with than, say, the ordinary chondrites. Yeah, and I'm completely biased, but this is a beautiful image. So what we found in the kind of initial sort of start, and this is still really early days for us with working with the Bennu samples, is that we find salts, what we would call salts. So this is an image, these little purpley grains, so the colours these are artificial colours, but that's a sodium carbonate mineral, let's call it trona. And so carbonates, so this is calcium and carbon and sodium in this one, are things that precipitate out of fluids. So this was liquid water at the start of the solar system on Bennu. And we find these carbonates. We've also found table salts, so sodium chloride, and we find potassium chloride, and a whole suite of different salts within these Bennu samples. And these are things that we haven't seen in our meteorites before. And that's because these things aren't very stable in our environment. So when our meteorite lands, these things get corroded and dissolve away and disappear really, really fast, so we never see them. But because these samples are pristine, they've basically never seen the atmosphere, we're seeing minerals in here that we haven't seen in our meteorites. And these tell us that Bennu had basically brines. The fluids were briny, and these are ideal environments. There's lots of chemicals within these solutions. They're perfect places for kind of synthesis of really simple prebiotic organic molecules.
And in fact, I mean, this is this work was published only a couple of weeks ago.
Yeah, really new this,
And there was another paper that said that they found amino acids,
Yep.
the kinds of things that make DNA.
Absolutely, yeah. So Bennu has about 4 weight% carbon, so it's really, really dark. I couldn't bring any with me, I'm afraid, I'm sorry. But it's so dark. I love the darker the rock, the better, as far as I'm concerned. And yeah, about 4% of it's carbon, and a lot of that carbon is organics, and they found, I think, I'm not an organic chemist, but I think they found 14 of the 20 amino acids that are used in terrestrial biology. They found all the nucleobases that are used to make things like DNA and RNA. So Bennu doesn't have life, but it has all those things you need, has all the kind of ingredients there, and it has the conditions with these briny solutions to start making complex organic molecules. And then these things were probably hitting the early Earth and delivering organics and delivering that water to the early Earth.
I think it's totally amazing. Very quickly, how far across is that?
Oh yeah, so there's a tiny little scale bar in the corner. So each of these kind of purple kind of needly things are about 10 microns or so.
So about the width of a child's hair.
Yes, yeah. So we always say human hair is about 100 microns, I think. So yes, that kind of, yeah. So really tiny. And these are things actually, one of the other reasons we do sample return is to kind of ground truth all that information that you get from the spacecraft. So OSIRIS-REx and Bennu characterize. We have a full geological map of the surface of Bennu, and we think we know lots about it, but without actually analysing the samples on the ground, we don't really understand what the mineralogy is. And these salts were things that we did not see at all from the spacecraft observations. We were not predicting these at all. So we really need samples to come back. We need to do all the amazing things with the spacecraft, but I'm completely biased. I would always say we need the sample as well to kind of really tie everything together.
So I'm going to come quickly back to you, Patrick, because I knew we'd do this. I've talked too much. There's too much to say. Can we bring Patrick back? And so you want to launch something in 2028 that will chase Apophis and catch up with it just before it flies over our head in April 2029.
Yes. So this is called the RAMSES mission, which is under development at the European Space Agency until formal approval at the ESA Council at ministerial level in November. You know, at the European Space Agency, every 3 years, all the member states of ESA meet together and discuss the budget. And we have the money to start the development because we need to launch in 3 years, which is tomorrow in the space business. So we couldn't wait this meeting to get the funding. So we have a pre-funding phase allowing to start the development, and we hope the formal approval will happen in November. And in order to speed up the process, we are using the same platform as a Hera mission. And basically we try to match as much as possible the design so that we don't have to start from scratch. And we cannot afford to start from scratch, both financially and in terms of time. And so the plan is, again, to have a main spacecraft with 2 CubeSats, launch in spring 2028, and arrive at Apophis 2 months before the closest approach to the Earth, which is April 13, 2029. So we'll arrive at the end of February, so that we can measure the initial properties of this asteroid, its shape, its surface properties, its internal properties, because we again have a radar, and see how these properties change under the influence of the tidal forces of the Earth during the closest approach. The beauty of it is that about 2 billion people, maybe more given the birth rate, will be able to observe the light of Apophis with naked eye over Europe and Africa. So in UK, if you have no cloud, you should see the light of Apophis. You should come to me.
Christine and General laugh, Patrick.
And in fact, what we want is to feed in live the real images of the asteroid taken by the spacecraft to the public. So you can imagine, children looking the light in the sky and on their smartphone, because they all have smartphones, a picture, real images of the asteroid, how it looks like really, and relate the two, which will remain the collective memory, such that, because of that, we submitted a resolution to the United Nations that was adopted in December to make of 2029 the International Year of Asteroid Awareness and Planetary Defense, so that we can organize around the world many events before the encounter to really emphasize the fact that there is no risk of impact. It's just, as you said, an opportunity which is extraordinary to better understand those bodies, and then to keep doing the work during the public events during the whole year, noting that, as was said, the OSIRIS-REx mission is now called OSIRIS-APEX for Apophis Explorer, and will reach Apophis a few weeks after the close approach. So we can do like we did with DART and Hera, but this time Europe arriving first and giving them the hand to US, who arrive a few weeks later, to continue the observations over 10 months. So again, this will be a great opportunity to show to the world how international coordination works. We have a lot of geopolitical tensions currently, and yet we are able at science level to keep working together for the best of science, and we'll have the world watching in 2029, so we have to show the good example and peaceful messages, and that will be a fantastic occasion. In fact, there are other missions that are under study, I would say, to visit Apophis, and we are tracking this because if we are more than 2 on the same asteroid, we better coordinate well, otherwise we may have a problem.
Just one, this is a personal interest for me. One of the CubeSat missions I heard about was the idea that you could put some seismometers down on the asteroid before it arrives. Is that, and then you could feel the shaking if it moves.
Exactly. So
is that going to happen?
For the moment, the study is going on whether we can land one of the 2 CubeSats or not, because the problem is the time scale. We have to launch in 2028, so everything needs to be ready 1 year before, and landing a CubeSat is not something which is trivial. So there is a study of that, and if it turns out to be feasible, then the plan is to carry a seismometer, which will landed on Apophis, and therefore when Apophis come close to the Earth, it may shake, and we can measure how the seismic waves propagate into the asteroid, which is another way to have information on internal properties. And that would be the first time we do seismology on an asteroid, which is a bit crazy. I mean, we need to do that because we have decades of seismology on the Earth, on the Moon, and even on Mars, and nothing on asteroids. So that would be the first occasion to do seismology on a body with very low gravity and see how the seismicity behaves in this environment. So I hope that the landing will be feasible. We'll know in the coming months, because that's effectively one of the plan. So seismology from the surface and tomography with a radar from another CubeSat flying around Apophis. These are two different ways to measure internal properties, with each of them having their limits. So combining the two measurements will really enhance our knowledge of the internal properties, which has many implications, not only for planetary defense, but also science. So it's really absolutely fantastic, and it's really also a good way to see how fast we can implement a mission, which actually for planetary defense is important, because in the ideal case, if an asteroid comes to us, the best is to be able to first send a reconnaissance mission that tell us what it is made of, so that we can better design the mission that has to deflect it. But we may be faced to the situation that we have to build quickly this reconnaissance mission. So training our ability to develop quickly missions is not only good because we are curious and want to build quickly, but also because of the need to be able to launch quickly a reconnaissance mission. And in fact, Hera was already developed only in 4 years, which is basically a record for a space mission to an asteroid. So we start with the basics.
Ashley, are you going to pay for them to bring some back?
But that's the problem with some. It's expensive.
But you'd like some, I guess.
But I would love some, yeah,
You'd love
absolutely.
some.
Yeah.
And Stefania, it's probably no one in this audience is going to be the right age to become a space navigator for this particular mission. How did you become a space navigator?
I think, first of all, I did space engineering at the university, but I think besides rocket science, I think you have to like math, computing, coding, and so it's mainly applied mathematics that is behind. So anything that has to do to try to solve real problem, which you can't necessarily solve by hands, but you need to use the computer to actually.
But at what point did you say, that's what I want to do? I just sort of feel that Patrick's got a job for quite a lot of people, many jobs for a lot of people in future to try and study asteroids better.
I did like maths when I was in high school, and in fact, my math teacher got offended when I decided to do engineering because she wanted me to become a mathematician. But for me, the joy I think it brings to do something practical, like using math for something practical, was much bigger. So I thought engineering was the right choice. And then I saw the specialization in space and I got fascinated. And so celestial mechanics was then the choices I made. So
Yeah, it's an amazing journey you've had. I knew we were going to do this, run out of time. What is the time?
It is 4:29.
4:29. I think, Patrick, thank you so much. And we're still safe. Nothing's changed.
Yes,
with
absolutely. You should better enjoy these bodies and what they tell us about our history than be scared. We are looking up for you.
Thank you so much for joining us, for bringing us that news. Thank you, both Stefania and Ashley. I think it's been totally thrilling. I expect there are people who have got questions for you, so don't run off, please.
yeah, sure.
All the best. Thank you so much.